For this problem, we're told that we have a first ionization energy for fluorine, and now we need to determine, well, what's the maximum photon energy of maximum photon wavelength I can use to ionize that fluorine. So first thing that we want to do is recall what ionization energy even means. This is the amount of energy you need to remove an electron. So it's to go from fluorine to fluorine positive plus an electron. Now, we've seen this before with electronic transitions, because we know that if we have some photon, we have some energy level of an electron, some photon's going to come in, and it's going to promote our electron somewhere. So we start from n equals 1, and we could go all the way up to n equals infinity, some high number. But if we get higher and higher up, we're just going to completely ionize this element. So it's the amount of energy we put into that electron to remove it. And that's great. However, the units are a problem because I have 1,681 kilojoules per mole. I'm not a big fan of those, so we're going to actually start from the units. So we're going to do 1,681 kilojoules per mole. And I don't want to go to per mole, I want one particular atom in question. I also want to get this in joules because I'm so used to working with energy units in joules, especially with electronic transitions. So the first thing I want to do, convert to joules from kilojoules, and those are going to cancel. And then I want to go ahead and get rid of my 1 mole to get atoms. So 6.022 times 10 to the 23rd atoms. And when I plug this into my calculator, I know I have 2.79143 times 10 to the negative 18 joules associated with 1 fluorine atom. So I need that much energy to get into the fluorine atom to completely ionize it. So all of this energy that you need to ionize it, this is going to come from a photon. And I'm going to underline 4 sig figs to be consistent. So all of this is going to come from a photon. So the energy of a photon is going to be 2.79143 times 10 to the negative 18 joules to 4 sig figs. And this is going to be equivalent to Planck's constant times its frequency, or Planck's constant times the speed of light over our wavelength, because the speed of light is defined as the wavelength of light times the frequency. If you ever see something that has 3 bars for equals, that is a definition. Okay, so speed of light is defined as the wavelength of light times the frequency of light. So I have all of this information, I have constants, I can plug everything in to get my wavelength, which is just hc over the energy of my photon. So 6.626 times 10 to the negative 34 joule seconds multiplied by the speed of light of 2.998 times 10 to the 8 meters per second. Divide this by my energy of my photon of 2.79143 times 10 to the negative 18 joules. And if you recall, we very rarely keep our wavelength in units of meters. We always like to try to keep our light units in units of light for nanometers. So I'm going to go ahead and do one last conversion. If you notice, your joules are going to cancel, and then the seconds in the numerator cancel, leaving you with just meters. So let's convert from meters to nanometers, which is going to be multiplying everything by 1 billion to get to my nanometers unit. And my wavelength here is going to be 71.163339 nanometers to 4 sig figs. So my wavelength that I need to do this is 71.16 nanometers. And if you recall back from the visible light spectrum, the lowest wavelength of the energy of light for visible is 400 nanometers. Anything less than that will have more energy, and that's going to be ultraviolet. So in order to ionize fluorine, you need ultraviolet light and this wavelength to do so.